658, lecture 15. So the last class we were talking about what is called differential operation, where so the basic idea was to take two identical circuits, operate them in antiphase as follows. If this happens, then we saw that any noise from, for example, the supply, okay, maybe there is some parasitic capacitance from the supply to the output. I mean, if these two are exactly identical, any parasitic that you can expect to be there from the supply to this output can also be expected to be there from the supply to the negative output. Only if I interpret my input and output signals not as absolute voltages on either of these nodes, but as the difference between these two voltages, then I can see that all noise sources which are common to both circuits will simply get cancelled out. So you can have, for example, a sensitive analog circuit operating on the same chip as a digital state machine, and the digital state machine is going to be switching at high speeds, causing lots of spikes on the supply. If, for example, one just used a single-ended circuit, so this is what is called a single-ended circuit because the signals of interest are the absolute node voltages. If I did something like that, if VDD was noisy, then we see that output will be what your intended output plus some fraction of supply noise. Okay. Now, if you operated two such circuits exactly in antiphase as shown here, then this noise source on the supply has the same transfer function to both outputs. So if I interpret my output signal as the difference between those two voltages, then all noise sources like the supply noise, which are common to both voltage circuits, will simply get cancelled out. Okay, so this is called differential operation. From now on, all our signals of interest will be not one signal but two signals, and the reason to do two signals is what I just described. So our circuits will have differential inputs as well as differential outputs. We don't have to get too worried about the fact that this circuit is talking to the next circuit. It's not really a problem because the next circuit also will take in differential inputs. I mean, the entire analog signal path is what is called differential. That avoids all noise on the common. You have two voltages. You can always express any two voltages V1 and V2 as V1 plus V2 by 2 plus V1 minus V2 by 2 and V1 plus V2 by 2 minus V1 minus V2 by 2. This is called the common mode component, and this is called the differential mode component. If you have a fully differential signal or a purely differential signal, what it means if you have two signals which are of this form, VCM plus VD, and the other one is VCM minus VD, where VCM is a constant, then these two signals are said to be. So if VCM is a constant, then you can see that the common mode component of these two signals is constant and doesn't vary with time. The differential component is VD and it varies with time. Let's say we had a system which had supply voltages of 0 and say 1.8 volts. I mean, generally, if we didn't use charge pumps and all this kind of stuff, comment on the absolute levels of voltage at any node in the circuit? If you didn't do anything deliberately to try and boost up the supply like we did in this Nakagome charge pump and so on, generally you can expect the voltages at any node to lie between 0 and VDD, or in this case 1.8 volts. Okay? So, even though you have these two differential signals, the absolute potentials of both these nodes should always lie between 0 and 1.8, okay, or VDD. If the supply voltage is VDD, what is the maximum peak to peak differential signal amplitude possible? Two VDD. How should you choose the common mode voltage to maximize the differential swing possible? Let's say I wanted to have as large a differential sinusoidal wave as possible, okay, and under the constraint that none of the absolute voltages exceed VDD or go below ground, then what would I choose my common mode voltage as? This is VDD, this is ground, okay, and clearly it makes sense to choose the common mode as VDD by 2, so that you can go up by as much as you can come down, and if this amplitude is A is simply nothing but VDD by 2, but this is the amplitude of the single-ended signal, right? So the peak-to-peak differential signal will be 2A, okay, because the corresponding negative signal will be doing. If I look at the differentials between these two waveforms, then the peak-to-peak amplitude is 4A 2 VDD. For instance, in a 1.8 volt supply, it is possible to have a peak-to-peak differential input signal of 3.6 volts. So that finishes the notion of what we call a fully differential signal. And what are we doing to signals? We are amplifying them, and we are putting them on capacitors and charging up capacitors, and then we are going into op amps and all this other stuff. This is VCM plus VD. This is VCM minus VD. So the difference between the two waveforms is 2 VD, which has an amplitude of 2A. Is that clear? So peak to peak it must be 4A. Is that clear to everybody? For example, you already designed sample and holds. For example, this is an example of a single-ended sample and hold. This is V in, okay, and this is running at some clock, and this is C1, okay. If you want to have a differential sample and hold, you have VCM plus V in. You have another guy, VCM minus Vn, and your output is not the voltage across any one capacitor, it is now the difference between the two capacitor voltages. So this is V out plus, let's say this is V out minus. So the output voltage, differential output voltage is V out plus minus V out minus. In general, as we saw, V out plus will have, the switch is not really ideal. So V out plus will have what all components? V out plus will have components at omega 1, 2 omega 1, 3 omega 1 and so on. What about V out minus? It will also have components at omega 1, 2 omega 1 and 3 omega 1 and so on. But what about V out plus minus V out minus? Only odd harmonics will be there. So, only odd harmonics. So, this is one important advantage of another important advantage of differential operation, namely you have gotten rid of all even harmonics. The next thing is to get to, so given any single-ended schematic, it is in general possible to copy paste the schematic on the side and operate one circuit with VCM plus VD, operate the other circuit with VCM minus VD, look at the outputs, take the difference and you are all set. One example that you have seen already, common source amplifier, alright, with an active load, a current source is the load resistor, so as to get large gain, and while in this circuit it looks as if current is being forced into the drain of a transistor, it's understood that this is going to be sitting in a negative feedback loop, so that there is some feedback from the drain to the gate which forces all of you are aware that you can't push current into the drain of a transistor. Is that clear to everybody? Now if you wanted to make a differential amplifier, where I'm not interested in multiplying the input voltage by incrementally by some value, the incremental input voltage by some value, but the incremental difference between two voltages by a large gain, okay? What would I do? One straightforward way is to simply, so this is VCM plus VD, this is VCM minus VD, the beginning of a simple operational amplifier as we have seen, right? Because an operational amplifier is going to be sitting in a negative feedback loop, and its job is to take the difference between the fedback quantity and the input quantity and multiply it by a large number. The job of the op amp is to basically gain up the difference between two voltages. For example, to make matters a little simpler, if I just call this R and call this also R, the quiescent voltage will be VDD minus IR, and then there will be an incremental voltage which is minus GM VD. Similarly, this voltage will be VDD minus IR, GMR VD, right? And lo and behold, the ratio of the differential output to the differential input is still GMR, as was the case for the single-ended circuit. A little thought will show you that if I wiggle VDD a little bit, then the gain from VDD to both the outputs is the same. So the transfer function from an incremental source on the supply voltage to the differential output is 0 because of cancellation. And in our earlier classes we have seen that you can in fact do better than this. Here we see that this circuit cannot distinguish between a change in the differential mode and a change in the common mode voltage. So if the input common mode voltage changes a little bit, what do you think will happen? Common mode changes a little bit, then we see that the bias current in the transistors increases a lot, which causes a large change in the output voltages, which could potentially cause these transistors to go into the triode region, okay, causing the gain to reduce dramatically. And the culprit is, we have seen in the analog circuits class, is that this way of biasing a transistor with a gate source voltage is a very unrobust way of biasing the transistor. A better way of doing it, and I will not go through the reasoning here, you can go and take a look at the video lectures on the analog circuits class, is to put a tail current, and this way for differential signals you get what you want, which is you get this node doesn't move, okay. So in this manner you do have differential gain, but you have no common mode gain, and you have gone and done all this common CMRR and all this other stuff. But the bottom line is that if I yank the common mode of the input up by a little bit, nothing happens to the differential gain at all, because the quiescent current flowing in both these transistors is the same. Okay, so this is also an example of differential operation, alright, but this is differential operation with a difference, in the sense that the common mode is actively getting rejected, alright. This circuit, for example, has got no common mode rejection at all, because if I yank VCM up, the output common mode will also go up. Without the tail current source here, just putting two common source amplifiers and operating them with anti-phase signals is also a way of getting rid of noise on the supply. Okay, but that has the danger of having in fact common mode gain, because if I yank the input common mode up, the output common mode goes low. Whereas the moment I add a tail current source, changing the input common mode, in principle, if the tail current source is ideal, has no bearing on the output common mode at all. So this is in fact better than just differential operation, okay, because this is actively rejecting common mode. And I think I have proved to you in this earlier analog circuits class, where not having common mode rejection can be a big problem. Okay, for example, if I had an op amp hooked up like this, the input differential pair didn't have any common mode rejection, then what do you think will happen? This is supposed to be unity gain follower. If this does this, this is supposed to do the same thing. So what can you say about the common mode of the input circuit doing the difference between the two voltages? This contraption, okay, without the tail current source, is sitting inside here, I say. If this is a good op amp, then whatever this is, this also must be the same. Can you make any comment about the common mode of that the input differential pair is seeing? The common mode signal is almost the same as the input signal. Correct? So you can see the input is a big swing signal, you can see the common mode will vary. This current source wasn't there, it will cause the quiescent currents in the transistors to go completely haywire and probably not cause anything, cause complete breakdown of the circuit. Does it make sense? Thanks to the current source here, we see that we are getting a large differential gain equal to GMR, alright? And in principle, zero common mode gain as long as the tail current sources. So far, we have been used to operational amplifiers whose output voltage is referred to which node? Output voltage is, when I say an output voltage is referred to some node, it means that it is taken with respect to that node. So in the standard op amp schematics that you are all used to and you have worked with in the labs, okay, the output voltage, you can't have an output voltage floating, right? A potential is always a potential difference. It's between two nodes. In an op amp like this, where is the other node for the output? It is understood to be ground. Alright? So this is what is called a single-ended op amp. In other words, the input is the difference between the two, but the output is referred to ground. So this absolute value is what you look at. If I wanted to build a fully differential op amp, what do you think the governing relationships must be? So in a single-ended op amp, okay, the absolute output voltage is a large multiple of the difference between the two inputs. In a differential op amp, the differential output must be a large multiple of the differential input. In other words, so the output voltage is now not any one node, but the difference between these two nodes. This is what my output is. Okay? And the input to the op amp is the difference between these two. And as usual, the differential output is some large number times the differential input. And what is the simplest, cheapest op amp that you can think of? What I've shown here. The differential output voltage, okay, is when you have a set of differential nodes, every set of differential voltages is associated with the corresponding common mode voltage, right? So, for example, here the two inputs are VCM, I call them I for the input. The two inputs are VCM I plus VD and VCM I minus VD. Okay. Okay, these are the inputs. And what is the output? PCMO minus GMRVD and PCMO plus GMR. And what is VCMO? VCMO is nothing but VDD minus IR. Okay, in this particular example, the gain you can get from such an op-amp is very modest. You make R very large. This is the same discussion we had with respect to active loads. If you remember, if you wanted a fixed current, you want to keep this fixed, okay, and the size of these transistors fixed. If you want a large gain, the only thing you can do is go on increasing R. If I go on increasing R, what will happen? The drain potentials will keep going lower and lower, and eventually it will push the transistor into triode. Okay, so a better strategy is to use a current source in place of a resistor. So to get better gain, what I would do would be to do this. What current should I put here? I. Is that clear? VCMI plus VD. This is VCMI minus VD. Now you can expect to get a substantial gain. The value of the gain should be how much? So if the transistors are in the active region, then the incremental gain will be GM times RO of the transistor parallel the RO of the current source. Okay. The crucial point is that the transistors will remain in the active region or in the saturation region.